This is section 3.1, vectors in the plane. You've already worked with vectors a little bit because a vector just looks like a matrix, but we didn't tell you what you were really doing. We let you add them, we let you multiply them by scalars, but in this section you find out what happens in real life when you do those types of actions. Section 3.1, vectors in the plane. All right, first of all, there are three representations of a vector. Three ways that we could write a vector. We could be talking about a physical vector, a geometric vector, or an algebraic vector. And I'll show you the similarities as well as the differences of these. First of all, a physical vector. A physical vector is a real-life event, such as a force or a velocity. It has both magnitude and direction. For example, I'm standing on the floor. I am exerting a force of 100 and however many pounds on the floor in a downward direction. Okay, or a velocity. You might be running at a particular speed in a particular direction. Okay, it has both magnitude and direction. Magnitude is like length. All right, a geometric vector is a directed line segment which can represent the physical vector. So in other words, I want to be able to draw a picture of the physical vector. And the geometric vector is that picture. Generally what's going to happen is you'll have a point, and a beginning point and an ending point, and then the segment that indicates direction in between them. For example, for V, which is equal to AB. Now that's the type of notation you'll see quite often. The first point is always going to be the beginning point, the second point is going to be the ending point, the one where the arrow is the one where it ends. And this is where A is the point 1, 1, and B is the point 4, 2. Okay, I just need to graph the point 1, 1, call it A, graph the point 4, 2, and call it B. Now draw the segment in between them and put the arrow at B so that you can see it's going from A to B. That is a geometric vector. A is the initial point, and B is the terminal point. So a directed line segment in the plane, or in 3D actually, we'll get to later, is a geometric vector. Okay, last, an algebraic vector. An algebraic vector is a matrix, and so you've seen these already. It's a matrix made up of a single column or a single row. We'll use a single column. Specifically, it's going to have an x component and then a y component. If the initial point is A, which is little a1, little a2, and the terminal point is B, which is little b1, little b2, then the x component is going to be the x's subtracted. Now notice when I subtract, though, I start with the terminal point. So I do b1 and then minus a1. Similarly, the y component is going to be b2 minus a2. So you subtract the y's, but you start with the terminal point when you do that subtraction. Very important. Okay, so if I have a point A, which is little a1, little a2, and B, which is little b1, little b2, and I have the directed line segment between them. So I have the vector AB. The way that this all works is that to get from point A to point B, I would need to go right a distance of b1 minus a1. And I would need to go up b2 minus a2. So you can see how this relates back to previous information you've had from geometry. To get from one point to the other, subtract the x's, that tells you how far right or how far left to go, and subtract the y's, that tells you how far up or down to go. All right, let's go back to the example we had before where V was AB and it went from the point 1, 1 to the point 4, 2. The algebraic vector would be, remember what we do is we subtract the x's, subtract the y's. So I want to do 4 minus 1, because 4 was the x value of the terminal point, and then 2 minus 1, because 2 was the y value of the terminal point, and I get 3, 1. So that is my algebraic vector. Okay, now as you see, to get from point A to point B, I'm going to need to go right 3 and up 1, just like the 3, 1 that I found from subtraction. All right, next, another example. Find the algebraic vector for v, which is AB again, where A is the point 2, -1, and B is the point -5, -3. All right, again, I want to subtract. I want to do the x value of the B first, so I want to start with -5, then minus the A, the x value of the A, so -5 minus 2. And then for the y, I would do -3 minus -1, which becomes +1. And I just get -7, -2. Okay, so not too bad at all. Remember, B1 minus A1, B2 minus A2. Two vectors are equal if their magnitude and direction are both equal. Okay, so in other words, if I have two things that point in the same direction and they're the same length, they're equal. Okay, the logic behind that is that I mentioned, myself standing on the floor is a force of however many pounds in a downward direction. Well, that's going to be the same whether I'm standing here, or if I'm standing on the table, or if I'm standing outside. I'm going to be exerting the same force. So the physical vector is essentially the same. Now, the location may be different, but that's not what we said. We said two vectors could be equal if their magnitude and direction are both equal. Okay, so they can be located in all kinds of different places and still be equal. To check whether two vectors are equal, we could compare the slopes and the lengths of the line segments. Okay, we said they have to point in the same direction, they have to be the same length. Well, to check the length, we'd want to use the distance formula, of course. To check the direction, though, we'd have to compare the slopes. And your good old slope formula is m is equal to y2 minus y1 over x2 minus x1. Now, we'd also have to check to make sure we weren't going from like lower left to upper right versus upper right to lower left. Okay, because the slope, it's going to take a little bit more than just the slope. We'll have to actually compare whether it's going, which direction it's going. The distance formula, of course, is subtract the x's, square that value, plus subtract the y's and square that value, and then take the square root of the sum. Okay, so we could go to this kind of trouble to check whether two vectors are equal, or there's a much, much simpler way. And the simpler way is just to compare the components of the algebraic vectors. All I need to do is really check to see if the x component's the same as the x component of the other one, the y component's the same as the y component of the other. So let's take a look at this example. If I have a equal to 3, -1, b equal to 5, 2, c is -1, 4, and d is -3, 7, I want to know, is AB equal to CD? Okay, now like I said, I could set up the slopes, I could do the distance formula and so on, but it's going to be much simpler to just find the algebraic vectors and compare their components. Okay, so if I wanted to do AB, I'd do 5 minus 3 and then 2 minus -1. So I get 2, 3 for AB. Now for CD, I again do the D component minus the C component. So I do -3 minus -1, 7 minus 4. I get -2, 3. Are they the same? No. 2, 3 is not equal to -2, 3. So AB is not equal to CD. Pretty simple, right? Okay, so just find the algebraic vectors and then compare them. Okay, next you need a definition, and this is called the position vector. The vector OP, and this is where O is the origin, is called the position vector for V. Now we need a position vector because we said that a vector can be located anywhere, right? It just has to have the same magnitude and direction to be equal to another vector. So for that reason, I kind of standard position for every vector. And that's what the position vector does for you. It gives you a standard position. So the standard position for any vector is to start at 0, 0, and end at b1 minus a1, comma, b2 minus a2. And that's always going to be true for a position vector. That's the definition. It's going to start at 0, 0, and end at b1 minus a1, b2 minus a2. For example, if a is -2, 1, and b is 1, -3, and v is the vector going from a to b, the algebraic vector would be, remember we start with the x value of b, so I'd do 1 minus -2, which is 3, and then I'd start with the y value of b, which is -3, and then minus 1, so I get -4. So the algebraic vector would be 3, -4. And if I wanted to do the position vector for that, you remember the components are b1 minus a1 and b2 minus a2. Well, the position vector is going to begin at 0, 0 and end at 3, -4. Okay, so good old AB went from -2, 1 to 1, -3. The position vector is going to go from 0, 0 to 3, -4. And as you can see, they're the same length and they point in the same direction, kind of southeast. All right, another example. Find D, where A is 3, -1, B is 5, 2, C is -1, 4, and AB is equal to CD. So I want to be able to find the point D. All right, now it said AB was equal to CD, so let's figure out what AB is. I want to do 5 minus 3 and 2 minus -1. That gives me the fact that AB is 2, 3. Okay, now I know that CD is also supposed to be 2, 3, but I need to give D a name, so I'm going to call D D1, D2. This is really the simplest way I've found to do this problem. You just turn it into an algebra problem, so that CD is going to be D1 minus -1, D2 minus 4. Okay, now that's supposed to be equal to 2, 3. So 2 is D1 plus 1, 3 is D2 minus 4. I wind up getting D1 is 1, and D2 is 7. So D is the point 1, 7. Okay, it becomes a pretty simple little algebra problem. All right, another example. This time we're looking for C. We again have that AB is CD, and A now is the point 0, 1, B is the point 3, -4, and D is the point 6, 2. I'm looking for C. Okay, now again, AB is equal to CD, so let's find AB. AB is going to be 3 minus 0, -4 minus 1. So AB is the algebraic vector 3, -5. Okay, let's give C a name. C is going to be C1, C2. So that I get CD equal to 6 minus C1, 2 minus C2. Okay, now go back and set that equal to what we got for AB. So I get that 6 minus C1, 2 minus C2 is equal to 3, -5. 6 minus C1 is 3, 2 minus C2 is -5. C1 is 3 then, C2 is 7. Just a little bit of algebra. Slide your C1 over, etc. So C is the point 3, 7. Okay, so that was section 3.1. Not too bad, right? We let you in on the big secret of what you're really doing when you're adding vectors and so on. We also took a look at what a vector looks like, equality of vectors, geometric vectors, algebraic vectors. Have a good time with this section. This is not too bad of a section, so spend a little time on it and everything will be good in this section.